When the Second World War began, infection was often deadlier than the battlefield itself. A soldier who survived a bullet or shrapnel wound could still die from gangrene, pneumonia, or blood poisoning. Medicine had no reliable weapon against bacterial infection. Amputation and hope were the only treatments. Yet within a few years, death from infection would fall by more than 90%. The reason was a quiet revolution born not in an arsenal, but in a laboratory flask: penicillin. Alexander Fleming had discovered the substance in 1928, noticing that a stray mold had killed bacteria on a culture plate. For a decade, the discovery sat dormant, its promise unrealized. In 1940, a team at Oxford University led by Howard Florey and Ernst Chain rediscovered Fleming's work and began testing purified penicillin in animals and humans. The results were astonishing. Infections that had always been fatal simply disappeared. But Britain, under bombardment, could not produce the drug in quantity. The solution came from across the Atlantic. In 1941, Florey's team carried a small vial of penicillin culture to the United States. There, American chemists and engineers turned a scientific curiosity into an industrial process. The U.S. Department of Agriculture's laboratories in Peoria, Illinois, developed deep tank fermentation methods that allowed the penicillium mold to grow by the ton. Pharmaceutical companies, Pfizer, Merck, Squibb, and Eli Lilly, joined forces, trading data instead of guarding patents. It was a wartime collaboration without precedent, competitors becoming allies to save lives. The challenge was biological and mechanical at once. Penicillium was fragile. Its yields were low. Scientists searched the world for better strains, eventually finding a superior one growing on a moldy cantaloupe in an Illinois market. Industrial fermentation tanks, borrowed from the brewing industry, were adapted to provide controlled aeration and temperature. Chemists learned to extract the antibiotic from vast vats of broth and crystallize it into a stable, injectable form. By 1943, American plants were producing enough penicillin to supply every Allied hospital. Its impact at the front was immediate. Before penicillin, 15% of all combat wounds became infected, and septicemia was often fatal. With penicillin, infection mortality in field hospitals dropped below 1%. Soldiers who would once have lost limbs returned to duty within weeks. Surgeons no longer feared deep wounds or abdominal injuries. Pneumonia, meningitis, and syphilis, all major military health problems, became treatable. The drug's quiet power was transforming not only medicine but morale. Wounded soldiers could now believe in survival. The military treated penicillin as a strategic resource. Early supplies were reserved for the armed forces, and doctors were instructed to recycle even urine to recover the precious drug. By D-Day in 1944, every Allied soldier carried the protection of penicillin through the medical corps. It saved tens of thousands of lives in Normandy alone, and countless more across Europe and the Pacific. The Axis powers, isolated from the discovery, tried to synthesize substitutes, but never succeeded in mass production. Behind the miracle lay a deeper transformation. Penicillin proved that biology could be engineered, that microbes could be harnessed as factories. It created the field of industrial microbiology and opened the path for later antibiotics, vitamins, and vaccines. The collaboration between universities, government, and private companies during the penicillin program became the template for modern biomedical research. When the war ended, penicillin's production lines did not shut down. They expanded. Civilian hospitals around the world gained access, and the once fatal infections of everyday life receded. Childbirth, surgery, and ordinary wounds became safe. The drug's discoverers received the Nobel Prize in 1945, but its true reward was measured in lives preserved. Penicillin did not win battles or destroy enemy armies, yet its effect on victory was undeniable. It kept soldiers fighting, reduced logistical burdens, and symbolized the humane side of technological warfare. It reminded a world consumed by machines that salvation could come from something as small and silent as a spore. It was the most compassionate weapon ever made, a cure forged in war, and humanity's proof that science could heal faster than war could kill. Mass production of penicillin became one of the greatest engineering feats of the war. What began as an academic experiment in a handful of glass flasks turned into an industrial network stretching across the United States. The task required solving problems that had never existed before: how to grow tons of delicate mold, how to extract its product without destroying it, and how to maintain purity on a factory scale. Chemists, engineers, and microbiologists collaborated under immense pressure, building a new kind of industry in less than 2 years. The solution lay in deep tank fermentation, a process adapted from beer brewing. Engineers redesigned fermentation tanks with precise temperature, aeration, and nutrient control, creating ideal conditions for the Penicillin mold to thrive. Yet even with perfect conditions, yields were low. The mold itself was unpredictable, sometimes weak, sometimes potent. The breakthrough came when researchers found a naturally high-producing strain on a rotting cantaloupe in a Peoria market. With this strain, production increased 100-fold. Extraction was another battlefield. Penicillin was unstable and degraded quickly in heat or acid. Chemists learned to isolate it using cold filtration and solvent extraction. At first, only a few milligrams could be recovered per liter of broth. By 1943, the yield had multiplied 1,000 times. Each discovery, better corn-steep liquor for nutrients, optimized oxygen flow, new crystallization techniques, pushed production closer to military demand. By 1944, American plants were producing more than 100 billion units of penicillin each month. The collaboration among private companies defied normal business logic. Pfizer, Merck, and Squibb shared research openly under government coordination. Patents were ignored. Secrecy gave way to urgency. Factory engineers worked side by side with academic biologists, translating laboratory protocols into continuous industrial operations. For the first time, biology was treated like engineering, quantified, standardized, scaled. The process became a model for every biotechnology program that followed. On the battlefield, the effects were visible in the statistics of survival. Before penicillin, 18% of soldiers wounded in action died from infection. With penicillin, that number fell below 1%. Field hospitals transformed from places of slow decay into centers of recovery. Penicillin-treated wounds closed cleanly. Operations once considered suicidal became routine. Amputations dropped sharply. The psychological effect was immense. Soldiers no longer feared the slow death of infection. Penicillin's influence extended beyond treatment. It transformed logistics and planning. Armies no longer needed to evacuate wounded men immediately. Mobile surgical units could operate close to the front, stabilizing casualties who once would have perished before reaching a hospital. Fewer deaths meant less strain on manpower and morale. The drug became as essential to Allied success as fuel or ammunition. The Allies guarded their advantage carefully. While German scientists understood the principles of antibiotics, the lack of resources and industrial infrastructure prevented them from achieving mass production. Japan's efforts were even more limited. By the time the Axis realized the scale of Allied output, it was too late. The miracle mold had already become a strategic weapon. By war's end, penicillin symbolized a new relationship between science and warfare. It proved that technology could heal as well as destroy, that the same industrial systems producing bombs could also produce cures. The campaign to manufacture penicillin changed not only medicine, but the very idea of what science could do under pressure. It showed that cooperation, not competition, could achieve the impossible. When the final battles ended and soldiers returned home, the factories did not close. They shifted to civilian production, flooding the world with medicine instead of munitions. In a war built on destruction, penicillin stood as its quiet opposite, proof that even in humanity's darkest moment, science could choose to save. By the final year of the war, penicillin had become not just a drug, but a symbol of civilization fighting back against chaos. It represented the idea that knowledge itself could be a weapon more powerful than any bomb. On every front, from the beaches of Normandy to the jungles of the Pacific, medics carried vials of the golden liquid that turned death into recovery. The number of lives it saved is impossible to count, but its influence reached far beyond the battlefield. In hospitals from London to Manila, wounded soldiers once written off as hopeless were standing again within days. Pneumonia cases that had killed pilots and submariners alike were now curable. Infections from burns, shrapnel, and surgery no longer spread uncontrollably through field wards. Even sexually transmitted diseases, a chronic military problem, were now treatable, restoring both health and morale. The change was so complete that it altered military medicine itself. Surgeons began operating more boldly, knowing infection would no longer finish what enemy weapons had started. Penicillin's victory reshaped the relationship between medicine and state power. The same centralized planning, mass production, and scientific cooperation that had built radar and proximity fuses now built a cure. The U.S. War Production Board coordinated every step, from corn processing to refrigeration. Pharmaceutical firms learned logistics from the military. The military learned medicine from scientists. It was a synthesis of war and healing, a reminder that industrial might could also serve life. After the war, the momentum did not stop. The facilities that had produced penicillin for the army were redirected to serve civilians. Hospitals worldwide gained access, and within a few years, diseases that had defined human suffering for centuries, pneumonia, meningitis, septic wounds, became treatable. Other antibiotics soon followed: streptomycin, chloramphenicol, tetracycline. Each traced its lineage to the same wartime laboratories and fermenters that had birthed penicillin. A medical revolution had begun, its origins not in peace but in total war. For the soldiers who lived because of it, penicillin meant more than survival. It meant proof that progress could still exist amid destruction. Letters home often spoke not of weapons or battles, but of gratitude toward a drug they barely understood. Generals credited it as a force multiplier equal to a new division. Statistically, it returned tens of thousands of men to combat and saved hundreds of thousands more from death. No other medical innovation had ever changed warfare so profoundly. Not by killing more efficiently, but by keeping men alive. In the greater history of technology, penicillin stands beside radar and the atomic bomb as one of the three decisive scientific breakthroughs of the Second World War. Yet it alone worked entirely in the service of life. Its success marked the beginning of modern pharmacology, industrial microbiology, and global health policy. It proved that the tools of war could be turned toward healing, and that the most effective form of victory was survival itself. When peace finally came, penicillin was already shaping a different world. Civilians received it by prescription, children recovered from infections once fatal, and entire hospitals reorganized around antibiotic treatment. The mold that had once grown unnoticed in a London lab now stood as a monument to human ingenuity. In the age of total war, it was the quiet revolution, the invisible salvation that fought not against an enemy, but against death itself. Allied victory depended on supply lines. When natural resources were cut off, chemistry provided substitutes. In the early years of the war, Japan seized most of the world's natural rubber. The loss threatened tires, gaskets, and many vehicle components. Synthetic rubber and high-octane fuel became strategic necessities. American chemists and engineers turned raw science into mass production. The problem was twofold. First, chemists had to create polymers that matched the elasticity and durability of natural rubber. Second, factories had to be retooled to produce those polymers at scale. Researchers built on pre-war advances in polymer chemistry. They optimized monomer mixes, improved catalysts, and developed continuous polymerization processes that kept product quality stable over long production runs. Production lines moved from lab benches to giant mixers and extruders. Quality control measures measured tensile strength, heat resistance, and aging. Tires and hose makers adjusted formulations to accommodate the new materials. Fuel presented a parallel challenge. Aircraft performance depended on high-octane aviation gasoline. Lower octane reduced engine power and increased the risk of detonation. American refiners developed catalytic cracking and blending techniques to boost octane. They substituted scarce aromatics with synthetics and designed additives that suppressed knocking. Engineers also improved storage and transport to preserve fuel quality across long supply lines. These chemical solutions required coordination between government, academia, and industry. The War Production Board prioritized feedstocks and allocated scarce metals and fuels to synthetic plants. Universities supplied process research. Major corporations converted textile and chemical plants into polymer factories. Licensing and technical data flowed rapidly. Patents were subordinated to wartime needs. The wartime ethic replaced competition with collaboration. The scale of production was unprecedented. Synthetic rubber plants produced hundreds of thousands of tons per year. Refinery expansions and new cracking units multiplied high-octane output. The raw materials included petroleum, coal-derived gases, and chemical intermediates. Supply chains for basic chemicals, like benzene and butadiene, were secured and expanded. Trains and tank farms moved feedstocks to plants, and tankers carried finished fuel worldwide. The logistic network itself became part of the technological achievement. On the battlefield, the effects were tangible. Trucks ran on synthetic tires without catastrophic failures. Aircraft performed at designed power levels and completed missions that would have been impossible with lower quality fuel. The standardization of materials simplified maintenance. Field repair units learned the new characteristics of synthetic compounds and adapted procedures. Replacement parts arrived on schedule because the industrial base could supply them. Limitations existed. Early synthetic rubber had different aging and wear profiles. Some products cracked in extreme cold, others were more prone to heat buildup. Engineers refined polymer blends to address these weaknesses. Fuel additives required careful dosing. Incorrect blends could damage engines. The rapid pace of production sometimes produced quality variation, but feedback loops from the front allowed engineers to correct formulations in weeks rather than years. The strategic consequence was decisive. Where resource shortages might have grounded fleets or immobilized armies, synthetic chemistry kept machines moving. Chemical substitution converted shortages into manageable engineering problems. The Allied ability to field motorized formations, airborne operations, and long-range air campaigns traced directly to these industrial chemical solutions. After the war, the techniques and plants did not vanish. The synthetic rubber industry matured into a peacetime sector. Refinery technology advanced civilian fuels and plastics. The wartime marriage of chemistry, engineering, and logistics became a model for future industrial mobilization. In the context of the war, synthetic rubber and fuel were not glamorous innovations. They were workhorse technologies. They proved that chemistry, when organized at national scale, could replace geography as a constraint on power. Synthetic chemistry's true strength during the war was its adaptability. Every shortage became a challenge of conversion. Natural rubber, once drawn from plantations in Southeast Asia, was replaced by polymers built from oil and gas. Every automobile, tank, and aircraft tire rolling through mud or snow carried the signature of chemical substitution. The synthetic rubber program began in earnest in 1942, when Japanese expansion severed Allied access to more than 90% of natural supplies. The United States launched the government rubber program, bringing together the major chemical companies: DuPont, Goodyear, Standard Oil, Firestone, and Goodrich. Rival firms that had once guarded patents now shared data and equipment. Within months, they built more than 50 new factories across the continent. Each plant produced one type of polymer: styrene butadiene for tires, neoprene for industrial seals, nitrile for fuel-resistant gaskets. The government financed construction, allocated raw materials, and coordinated transport. Industry supplied labor, machinery, and scientific expertise. By 1944, synthetic rubber output had surpassed 800,000 tons per year, completely replacing natural imports. Tank convoys, jeeps, and bombers relied on it. Allied logistics operated on a foundation of chemistry. Tires no longer depended on plantations or shipping lanes. Instead, they emerged from pipelines and reactors, proof that industrial networks could outpace geography. Fuel chemistry advanced in parallel. The introduction of catalytic cracking and alkylation transformed aviation performance. These refining processes, accelerated by wartime necessity, produced gasoline with octane ratings above 100. That single leap in chemistry increased aircraft power, range, and reliability. Fighters climbed faster and bombers carried heavier loads. Engineers learned that chemistry could multiply the effectiveness of machinery without redesigning the machinery itself. Synthetic lubricants and hydraulic fluids followed. They resisted freezing at high altitude and thinning under heat. Jet engines and long-range bombers benefited directly. The cumulative result was not spectacular like a new weapon, but pervasive, a quiet enhancement across every system. Chemical plants became part of the war's infrastructure of endurance. Where other industries built things to destroy, chemistry built materials to survive. Synthetic fuel and rubber were invisible to soldiers, but without them, the machines of war would have stalled in the mud. Their development required coordination on a continental scale, railroads feeding refineries, refineries feeding reactors, reactors feeding factories. By the war's end, the Allied ability to sustain mechanized warfare anywhere on Earth was no longer tied to resource luck, but to chemical knowledge. Synthetic production had replaced colonial dependency. The war proved that control of molecules could equal control of continents. It marked the point where chemistry ceased to be an auxiliary science and became an engine of strategy. The triumph of synthetic chemistry during the war was not a single invention but a transformation of scale. By the final year, the chemical industry had become a second army, quiet, invisible, and continuous. It fought through laboratories, pipelines, and furnaces instead of trenches. Every convoy, air raid, and mechanized advance relied on it. The war had begun with shortages and ended with surpluses, because chemistry had turned scarcity into a solvable equation. Synthetic rubber was the clearest proof of this transformation. Its production had surpassed 1 million tons annually by 1945, feeding every front. Engineers no longer worried about losing supply lines from Southeast Asia. Tire factories ran day and night, blending polymers with carbon black and new stabilizers to create compounds that outlasted their natural counterparts. Each formulation, some softer for transport, others harder for armor vehicles, was designed with mathematical precision. Laboratory control, not geography, determined the pace of movement. Fuel chemistry carried the same logic into the air. Catalytic refineries and alkylation plants delivered a steady flow of high-octane aviation gasoline. Each barrel represented the work of thousands, chemical engineers adjusting temperatures by degrees, operators balancing reactions, and inspectors ensuring purity to the last molecule. The result was flight reliability. Engines burned hotter and cleaner. Fighters and bombers that once struggled for range or altitude now exceeded both. The chemistry of octane had become a weapon of endurance. These synthetic processes reshaped labor and knowledge as well. Chemists became strategists. Universities trained thousands of engineers in polymer and petrochemical design. Wartime laboratories, at DuPont, Standard Oil, and the Bureau of Mines, formed the core of the post-war plastics and energy industries. The same catalytic beds that produced aviation fuel would later generate the polymers of the consumer age: nylon, polyethylene, and polystyrene. The war had forced chemistry into full maturity. On the front lines, the effects were rarely visible, but always felt. Tires resisted tropical heat and Arctic cold. Fuel stored for months remained stable. Mechanical failures dropped, and mobility increased. Commanders could plan campaigns without fearing resource collapse. Synthetic rubber and fuel had transformed logistics from vulnerability to weapon. They did not destroy the enemy. They simply ensured that nothing the enemy did could stop the machinery that would. After 1945, the chemical empire built in wartime became the foundation of modern civilization. Synthetic materials filled every home, laboratory, and factory. The same plants that had supplied armies now supplied economies. In the long arc of history, the synthetic rubber and fuel program marked the moment humanity learned to manufacture nature itself. It was chemistry's quiet victory, unseen in battle, but decisive in outcome. The war had proven that equations could replace empires, and that the mastery of matter was the surest route to power.